That's very good. I was worried after day one there'd be nobody here for day two. So, okay, we have another 2 hours together, and I'm going to try and break it into two pieces so we get a little bit of a break halfway through. Here's the topics that I'd like to cover today. So we're going to go through a little bit more about the properties of functional MRI data, just very basic ideas of questions one can ask using bold fMRI. And so that'll be under the category of inference. So that's really the relationship between a good brain picture and some claims that you can make about the mind and behavior and things like that. And then we're going to start talking about more of the details of how you design a good fMRI experiment. And to talk about those things, we're going to first need to understand this thing called the Fourier Transform. So I've written it up there. I'll run through a little demonstration on the whiteboard here of how to think about the Fourier Transform. But again, there are good demonstrations on the internet as well, if you want to see it in animation on a computer, so you can see it that way. And so once we know a bit about the Fourier Transform and a way to talk about signals in time and in terms of frequencies, then we'll talk about the signal and noise properties of functional MRI. And that includes understanding a bit more about the hemodynamic response function. That's the response of blood flow to a change in neural activity, and a little bit about the 1/f noise. So this is the noise that's present in bold fMRI data when subjects are at rest. And it turns out this noise is critically important not only for designing experiments and knowing what kinds of modulations or changes of neural activity we can detect, but also in the modern era, in the last few years, we know that this noise is the basis of the resting state connectivity, the source of a lot of very interesting studies looking at how different cortical brain areas communicate with one another when people are at rest. So we'll talk about signal and noise. And then understanding these principles, let us understand how to design fMRI experiments to produce neural changes that we can measure. So that will be design in time. And then finally, we're going to talk about perfusion fMRI. It's a different way of getting a measure of changes in neural activity, and it's one that does away with one of these constraints. So using perfusion fMRI takes away this noise, this 1/f noise stuff. And so it means that there's certain things you can do with perfusion fMRI that you can't do with bold fMRI. So that's the menu. That's what we're going to try and cover in the 2 hours today, plus a break. So that shouldn't be too bad. Okay. So, and again, please interrupt for questions. This is, it's hot in here. It's a very long session, so ask questions and then everybody else can take a break and listen to you instead of me. Okay, so this is where we left off last time. So we had talked a little bit about the properties of the bold fMRI signal in time and in space. And so just to refresh your memory, what's shown here is the hemodynamic response function, right? And this is what comes from thinking about bold fMRI as a system, as a linear system. And this is the output in time from one point in the brain to a brief period of neural activity at time 0, right? So no activity, and then brrr, some neurons fire, and then you get this change in blood flow that takes about 12 seconds to rise and fall and come back down, okay? And so this property of bold fMRI means that it is hard for us to detect things that change quickly, right? So fast changes in neural activity are hard to measure because this thing is very slow, right? The plumbing of the brain is slow. So like when you flush the toilet, it takes a while for the water to flow up and then flow down again. And so in the same way, when the neurons go, it takes a while for the blood to come up and come down again, okay? And so that's in time, and then this is in space. So a point of neural activity right here leads to a spread of blood flow, which spreads over 3 to 4 seconds. These are very basic and important ideas for as we move forward. So let's stop for a moment and see if there's any leftover questions from yesterday about these basic ideas. You guys are a very obedient audience. There's no questions at all. Okay, well, so this is what we're going to build from then. Okay, so what I'd like to run through now are just thinking a little bit about sort of, oh yes, great. I can.
So you were talking about the hemodynamic response and the linear relation between the neural activity and the hemodynamic response. Mm-hmm. So in principle, this hemodynamic response could be considered as a direct reflection of every neural activity that I have in the brain.
Including, given that it filters, it's a filter, but yes, okay. So it's going to, there is a blood flow change.
But there will be regions of the brain with different hemodynamic response functions.
Okay.
Compared to others. So we know all the hemodynamic response functions
yeah.
of all the parts of the brain, or we estimate them.
Okay, good. That's right. So I think when we left off yesterday, there were some remaining questions about variability in this response, right? How does it vary across different people, and how does it vary across points in the brain? So that plot there is the average hemodynamic response function measured from motor cortex, so up here. So we know that the hemodynamic response function varies across people. So different people have different shapes of hemodynamic response functions, but that they are all quite similar. So there is a family of responses that all of us have that all have the general shape of rising, peaking somewhere between 3 and 6 seconds, and then falling. Okay? So there's variability, but then there's also a common shape that we all have. Then there's the question of, does the hemodynamic response function differ from brain regions? And what I had mentioned yesterday was that there is some evidence that that's true, but it's a very difficult question to test, because to even ask the question, it requires the ability to produce very brief, instantaneous neural responses in different parts of the brain. And so you can do that for the visual cortex, and you can do that for auditory cortex, but how do you make that happen in prefrontal cortex? What's that? You stimulate, so with a wire or a TMS. Yeah, that's right. So that's right. Then here is an experimentalist. Yeah, that's right. So the only way to really answer that question is to go in and produce the neural activity, not by behavior, but by an experimental induction of current. And so those studies have been done in animals, and there's one study that I know of like that in people. Anyway, it's a long story, and it looks like there are some small differences in the shape of the hemodynamic response function. You know, in particular, in early visual cortex, it looks like this shape is a little bit narrower in time, so it's a little quicker. And it looks like this spread is a little smaller back in primary visual cortex compared to other visual areas and other parts of the brain. So there is some differences, but the truth is, most of the time, it's for designing experiments and analyzing data. If you just assume the average, you'll do okay. There are very few experiments where knowing exactly the shape of the hemodynamic response function matters. I will mention two types of experiments, though, that depend upon knowledge of the hemodynamic response function. And both of those sorts of experiments are ones in which you're trying to make very precise claims about the timing of neural activity. So if you wanted to claim, for example, that one part of the brain had neural activity before another part of the brain, okay, that would require that you would know exactly the shape of the hemodynamic response function in those two parts of the brain. And so in general, that kind of study can't be done with fMRI. You can't claim that this part of the brain had activity before this part of the brain, right? Because that would have to assume that the transformation was the same. And in a similar way, I know I must tread cautiously here. There is a field of experimental design called dynamic causal modeling, which is a technique to look at the connectivity between different areas of the brain and to attribute a directional effect of one area of the brain influencing another area, influencing another area. And those techniques make assumptions about the shapes of the hemodynamic response function and the ways in which they can vary. And so that's a technique that makes some strong assumptions about knowing the shape of the HRF and the ways in which it can vary. And so there's some question as to whether or not those assumptions are right or wrong. But in general, that's another technique that requires precise knowledge or assumptions about the HRF. Okay, got it? All right. Okay, so now we're going to talk about, so that was very dynamic causal modeling and timing of brain activity. It's like fMRI graduate level. We're going to come back to now fMRI 101. So let's just talk a little bit about some basic types of experimental design and the kinds of designs that you could do with fMRI, with bold fMRI, and some sorts of experiments that would really stink. So if nothing else, I'd like to have you learn today about types of experiments that would be really bad. So don't do these experiments because you'd never find anything. You'd never get a good result. Okay. So again, remember that when we talk about functional MRI studies, we're dealing with two systems, right? There's the system one. This is the system we want to study. That's the relationship between stimuli and behavior and neural activity. And then system two, this is fMRI over here. This is what lets us go from a picture of the brain back to neural activity and then make claims at this domain, right? So again, I want to remind you of that model as we go forward. Okay, so let's talk about a prototypical experiment. So this is like a typical kind of brain image that might result from an fMRI study. And it turns out that this brain image comes from a person who's notorious in the United States. And this is the brain of a guy who is a convicted killer. So people in the United States know who this guy is. His name is Dugan, Brian Dugan, and he was a murderer in the state of Illinois. And he was a terrible guy. He committed a bunch of horrific murders and then killed a policeman. And anyway, they finally caught him, and they put him on trial. And they found him guilty for all these terrible crimes. And then Illinois is a state that still has the death penalty. And so they were considering in the next phase of the trial whether or not he should be executed for his crimes. And in the United States, in criminal cases, when they're considering the death penalty, the lawyers are allowed to present any evidence they want to try and convince the jury not to give the death penalty. And so in Brian Dugan's case, they brought in a guy named Kent Keel, who is a scientist who studies criminal behavior and psychopathy, psychopaths. And so Kent's claim was that, so he took Brian Dugan and he did an fMRI study on him. And his claim was that when Brian Dugan saw pictures of faces with emotion, right, so angry faces and sad faces, that Brian Dugan had less of a response to those emotional faces than do typical or normal people, and that based upon Kent's results, that would then support the claim that Brian Dugan, this guy, is a psychopath. You know, a psychopath is someone who has no, it's a behavioral definition of a psychiatric disorder, someone who has no emotional response to other people's suffering, for example, has no empathy. Okay? So Kent claimed, the scientist claimed, that because Brian Dugan had less of a brain response to emotional faces, that therefore he was a psychopath, and then he should be spared execution. Now, I don't actually know why, if you're a psychopath, that means you should or should not be executed. I don't understand all those details of that defense. But we can examine this claim, right, that because there's decreased brain activity or decreased fMRI response to emotional faces, that therefore we know that this guy is a psychopath. Okay? So that's the claim that was made in court and that we're going to examine a little bit and think about fMRI experiments that could or could not examine that kind of question. Okay? All right, so that's the claim. Psychopaths show reduced responses to emotional stimuli within the amygdala. right? That was the claim that was made. So how is that claim done? Well, so the first thing that everybody in this room probably knows about functional MRI experiments, but it's worth pointing out explicitly, is that these claims are never done about just emotional stimuli themselves. It's always a comparison between two things, right? So oftentimes, the description of a study will be, oh, we showed this is the brain area for love, or we showed that this is the brain area for conflict resolution, right, or for noun selection. Well, it's always noun selection versus something else, or conflict resolution versus something else. So this might be a prototypical type of design which would be used for the kind of question we're talking about here. For example, they might have had this, this killer in the scanner, and then over time presented pictures of fearful faces and then neutral faces. Actually, this looks kind of angry to me, but he's supposed to be neutral. Okay, so fearful faces, neutral faces, fearful faces, neutral faces, and the idea is that the fMRI signal will go up during the emotional phases and then down during the neutral phases and up during the emotional and down. And so that might be from one spot in the brain. And so that's the signal over time from one location, right? And the signal rises and falls with respect to the stimuli that are presented. Okay, so that's the first kind of claim, is that when you say that there was an increased response or that there was a response to fearful faces, it's fearful faces as compared to, in this case, neutral faces. Okay? Now, because we know the shape of the hemodynamic response function, or we're willing to assume a shape for it, we can predict if there was a brain area that had increased activity for the fearful faces and decreased activity for the neutral faces, that there should be a blood flow response that should have that kind of shape and fit it. Okay? And so then, the way we get from this kind of signal over time into one of those brain pictures is you do something like this. You say, okay, for one point in the brain, how big was the difference between these two conditions, right, between the fearful faces and the neutral faces? So you just take the average over all the times that you did it. You say, how big was that difference, or how reliable was that difference with a statistical test? And then you make a color-coded map, right? So you say, okay, for that point in the brain, that difference was, oh, that was kind of a small effect. And you put that down, right? And we could do this as just a number. We could say, oh, well, it was 3% signal change, or we could say it was with a statistical test, a p of 0.005, and write that number down in the little box. But we couldn't read all the little numbers. They'd be too small. So we use a color code approach. So you put a color dot down. But you do that for every point in the brain, right? So poof. So every point in the brain gets a color corresponding to how big that effect was. Okay? And this is then the basis of these statistical maps that are shown. And this approach is referred to as a massively univariate approach. That is, for every point in the brain, you test the idea that there's a difference between condition A and condition B. Okay, and that gets called, it's a univariate statistical test at every point. So it's massively univariate. Okay, so, and again, the point here is I'm going to walk you through just some very basics about how you go from the signal into a brain picture. Okay, and we're going to come back to look at this in more detail and with more technical information. So, okay, but this is what you're starting off with. But then here comes the stage that I sometimes call Neuro Aesthetics, which is going from that sort of initial test into a pretty picture that looks good on the cover of Science magazine. And the way that goes is something like this. And it's interesting because every step is very well justified, but it ends up with making a picture which is pretty different from the original data. Right? So you start off with this image of the brain where every point is a statistical measure of the difference between the fearful faces and the neutral faces. But, not all of these points are a real difference, right? Some of those are just noise. It's just, there's random fluctuation. You're only interested in those points where there was a big difference or a significant difference between the two. So we engage in a process of thresholding. We say, okay, well, we're going to say only differences bigger than this are ones that we believe. And we're going to come back to how you pick that threshold and what determines that threshold. But you set a threshold and say, only show me those points that are above the threshold. But then additionally, for for perfectly good statistical reasons, you also want to smooth the data in space a little bit. So we'll talk about that. Technically, actually, that smoothing is done on the raw data, not at this stage. But it's normal to take the data and apply some degree of digital smoothing, so smooth the data over space. Okay? And this is done because it's easier to detect signals which are the size of the amount of smoothing that you applied. It improves your statistical power for those things. Okay? But that has the effect of it makes it easier to see big things and harder to see small things. That's the effect of smoothing in space. Okay? All right, that's looking better. But you know, it's kind of hard to see where this blob is on the brain if I just show it on top of that fuzzy echoplanar image. So how about I display that on top of a T1 weighted image? Ah, that's better, right? So now I can see that blob on top of this T1 weighted image. It's much clearer to see kind of where in the brain it is. But then, of course, the final problem is that this is just one slice through the brain, and the brain's a whole volume. So how do I show the whole volume of the brain? Well, that's where you then do a digital reconstruction. And you sort of get a 3D, and you cut out a piece. So that's right. So this is how data ends up getting presented in fMRI studies. Right now, this is ready for Nature. But you know, it's a long way from what the data started off on. It's very interesting. It's not something that I'll talk much about during our time together here. But I think actually as a field, there's a certain aesthetic. There's a certain way that we all expect brain pictures to look. And we expect them to look like this with like a smooth blob that's positioned in the brain. And I think it's an aesthetic that's guided by wanting the activation to look organic, like it could have grown there. It looks like it's about the same shape and size as like a tumor or something. It looks like it could have grown there. So I think there's definitely an aesthetic that is expected. But in any event, the way we end up with one of these pictures is each of these are very well justified statistical steps that we take. And we're going to come back to each of these. Yeah?
Are you claiming, it's funny that in the graduate schools there should be a model that says how to make pretty beautiful brain imaging pictures with free surface?
Yep.
And with,
well,
because if you don't get this kind of surface and
right.
plated brains, and usually you don't get a bigger natural PNAS.
Yeah, I think, well, yeah, I think it's true.
Actually, the important result is the one in the middle.
Well, yeah.
Is the one which is less effective.
Well, yeah, I think it's, well, it's a very interesting topic. And I think that, you all know that Nature Neuroscience, the images that are presented in there they have to look kind of nice. I mean, they got to be pretty pictures, right? And I think there is just and it's never, I don't think it's ever explicitly stated. I don't think it's ever the case that, brain pictures must have a certain level of smoothness and they must have only 1 or 2 blobs, but not 10 blobs. 10 areas of activation, that's too many. 1, that's too few. 2 is just about right. It's never explicitly like that. But I think that there is, it's a culture. And we've all been sort of trained in this culture that brain pictures look a certain way. And I think it's had interesting effects. I think that it has led to, it's one reason why multivoxel pattern analysis as an alternate technique took a really long time, I think, to come along. Because people were very sort of focused on seeing brain pictures that had a certain look. And multivoxel pattern analysis, that works with data down at this level, not at this level. So I think actually that aesthetic is there, and I think it's had consequences. But, it's an interesting aspect of the culture, but I think one that is changing over time as we move into, other sorts of ways of analyzing the data. So, but in any event, but I want to introduce this as a schematic because as we go along in the next couple of days, we can talk about how these thresholds are set, how you decide how much smoothing to do, and then we will talk less about sort of the 3D presentation of data. But those earlier steps are going to be important. Okay. One other step that is used is that this is the data from now just one subject. So then how do you combine data across subjects? So you might have data. These, by the way, are all cartoons. These aren't real data. So you might have this kind of set of results from 10 subjects. And so, 10 subjects did the experiment, and everybody had, some kind of activation. But how do you combine that data across subjects and make a statement about what's true about the group? And then that involves somehow taking different brains and aligning them to a common spatial atlas, a common brain atlas, and then combining their data. And that's something as well that we can talk about a little bit, how it is you sort of make that decision how to align data. And there's techniques that have been around for a little while that use the brain as a whole volume, which is made of kind of a rubbery, like you treat the brain as if it was a rubbery material, and you can stretch it to kind of get different brains to match together. And there's also techniques that look at just the cortical surface of the brain and align those. So there are different ways of solving this problem of taking variability across subjects and combining them, but nonetheless, this is a necessary step if you want to make a group point. And so oftentimes, the end result is that you have some group comparisons. You take all your 10 subjects and you align them in some way, and you create something like this. Okay? So the end result then for something like this is a plot like this, which is that if across a group of 10 subjects, so this is actually the data that, this is the actual kind of claim that the scientist who testified in court brought to bear. So this is the study that he had done. So if you look in the amygdala and you have subjects look at fearful faces and neutral faces, and then if you take 10 psychopaths, right, so 10 people who are criminals and are in jail, and you scan them, and 10 normal controls, and you look at the difference between fearful faces and neutral faces, the average across 10 subjects looks like this. So this is the 10 normal people, and this is the 10 psychopaths, and the difference between those two things is significant, right? So that's the claim of Kent's study. So we can now think about this first kind of claim, which is that, okay, is it the case that psychopaths as a group, right, that these criminals as a group show reduced responses to emotional stimuli within the amygdala? And that seems like that's well supported, right? That seems like that's true, because I've now replotted the data from, or the cartoon from the prior slide. So if this is the distribution of fMRI responses across subjects, right? So this is having a small response to fearful faces, and this is having a big response to fearful faces. And this is a histogram of the psychopaths, and this is a histogram of the normal controls. You can see that those two curves are different, right? So psychopaths as a group are different from control subjects. But what about this claim, which is that this guy is a psychopath, right? This one person is a psychopath. So for that to be true, you have to get a measurement from one person, right? And then know, based upon this data, if he falls into the psychopath group or the normal group. And so suppose for that killer, Brian Dugan, if you had scanned him, his response to emotional faces would fall there. So is he a psychopath or is he a control? I don't know. He's kind of more psychopath than normal, but he also falls within the normal range, right? So in any event, this is not a problem that is, or an issue that is unique to neuroimaging, but when oftentimes in neuroimaging studies we make claims about groups, and it's a very different thing to make a claim about a group as compared to a claim about an individual person, where you then have to deal with the distribution of responses across a population. All right, so I might have gone through that a little fast, but let me see if there's any questions about this idea from the audience. Yeah?
You argue that psychopaths have lower activity for emotional stimuli. It can also be the case based on your graph that they have higher activity for normal.
Exactly, right. So again, these are, so the question was, hey, oops. I made a plot here of the difference between fearful faces and neutral faces. So it's the difference between the two. But it's also possible that what's happening is that the psychopaths just have more of a response to neutral faces as opposed to a reduced response to fearful faces. And we don't have a way of testing that idea without having a third condition to which we can compare this, right? So for example, some putative neutral state or rest state or a state of looking at a blank screen that we could compare those two things to. That's right, so we only have the difference between those two things. So again, all of these measurements are always made as a comparison between two things. We're going to talk about in a moment, or in a little bit, perfusion imaging as a way to avoid this challenge of having to always compare two things directly together like that. Okay, so with this sort of as a prototypical experiment, let's run through kind of some of these ideas about how it is you could design an experiment to measure these effects and ways that you couldn't. All right, so here's a prototypical experiment, right? So here's what you want to do. You want to measure a magnitude of neural response within the cortex to a standardized emotional stimulus in a group of subjects, right? So this is this classic design that we've talked about. And so this example experiment I've described illustrates a few of these properties of functional MRI, that it's a relative signal. You always have to compare between things. I'm going to talk a little bit about how it's an indirect measure of neural activity, right? It's not actually a direct measure of neural activity. You're measuring a blood flow change. We're going to talk about how you're measuring a bulk activity change or an average change across neurons, not a neural pattern itself. And we'll talk a little bit about subtraction designs and blocked ordering of stimuli. So this is some properties of this experiment or this type of experiment that I wanted to illustrate. Okay, so coming back to this idea of a relative signal. So here's an experiment that wouldn't work, right? So the goal might be to determine if the bold fMRI signal during emotional face perception, just emotional faces, is reduced in psychopaths compared to controls, right? So here's an experiment that wouldn't work, which is that you take 10 psychopaths and you put them in the scanner and you have them just look at fearful faces, right? And then you take 10 subjects and you put them in the scanner and you have them just look at fearful faces. And you just measure that average signal, right? And you'd like to find something like this, that just the raw fMRI signal is bigger for controls than for psychopaths while looking at those fearful faces. And why doesn't that work? Like, why can't you just directly measure the emotional face response itself? Why do you always have to compare it to something? And the reason is that we are measuring a hemodynamic proxy of neural activity, right? We're not actually directly measuring neural activity. We're measuring this other thing, this bold fMRI signal, that's the result of these chain of events. And one property of that is that the bold fMRI signal has no absolute direct interpretation, okay? So the numbers that come off of the scanner for the bold fMRI signal, they don't have units that have meaning in terms of a physiologic process. It's not in units of blood flow or spikes per second of neural activity, okay? They're, in a sense, arbitrary units, or they're units that don't have a direct interpretation in this way. And that number, the actual number that comes off the scanner, the measure of the bold fMRI signal, it's influenced by lots of things. It can be influenced by sort of your breathing. It can be influenced by how much dental work you have in your mouth, right? Because if you have a lot of metal amalgam in your mouth, that's going to alter the local signal. So the bold fMRI signal has no direct absolute interpretation. You always have to compare two things, okay? So we know it's an indirect measure. So that first kind of experiment, that wouldn't work. So now we know what we need to do is this kind of thing where we control or compare the fearful faces to a neutral control. And so now what we're going to try is an experiment where you look at the signal change, the difference between fearful and neutral faces for controls and psychopaths, okay? And the goal, again, is, as we saw before, to look at that difference between the two groups. Okay, so how could that go wrong? Well, it could go wrong for other reasons, and that is that because we're measuring a hemodynamic proxy of neural activity, if there's something that would make those two groups different in their blood flow responses, then that's another way that you could think that there's a difference in neural response between the groups, but actually it's just a blood flow response. Suppose psychopaths as a group tend to use drugs, and those drugs alter a blood flow response. Okay? And this is certainly true for any kind of comparisons between groups that differ in age or gender, the drugs they take, hormonal status. Any of these things can modify the shape of the hemodynamic response function and thus would make this claim of a group difference suspect. Okay? A way to kind of get around that problem is you might have in your experiment another kind of comparison where you don't expect there to be a difference between the groups, right? So if you showed, for example, that the psychopaths and the controls have equal responses to a flash of light versus darkness, then you'd say, okay, well, that control experiment, they're the same, but for the emotional faces, they're different. Okay? So that additional test is necessary to compare groups. The other problem, of course, is that when you make these claims from just one study that you've done, you have to make sure that the group that you've tested is a generalizable result. Most of the studies we do are on healthy college students, but that doesn't mean that that result is the same for other groups like middle-aged lawyers or kids, right? So again, we have to be cognizant of the fact that many of these studies are done on one type of group, but can't be extended automatically to other groups. All right. So then finally, here's another way that there might be a difference between the two sorts of stimuli that you might have trouble measuring with functional MRI. Okay? So again, the design is we're going to show emotional faces and neutral faces and look for the difference between them. There are some kinds of ways that two things might be different in their neural representation, but that you might not be able to detect it with fMRI. And one way that can happen is if it's not a bulk neural change or an average neural change. So let me describe what I mean by that. Okay, so this is a cartoon of a little patch of cortex, maybe just a little 3 millimeter bit of cortex, and those arrows are neurons, okay? And the height of the arrow is how much those neurons are firing. So to be able to detect a difference using fMRI, it must be the case that there's greater neural activity on average for that piece of cortex between the two states, right? So the fearful, I've got that backwards, darn it. The fearful faces here, imagine that's the neutral face. The neutral face has a small response. The fearful face has a big response. That would be detectable. That would be a difference in average firing. What's undetectable for fMRI is a change in what we might call the population code or the pattern of firing, okay? So if this is a little piece of cortex with some neurons, and here's another piece of cortex with some neurons, in both cases, the piece of cortex responds to the stimuli. It's just a different pattern of neural firing for one stimulus for the other. So on average, the average signal here and the average signal here is the same. So you would not see that as a difference with bold functional MRI. So actually, let me pause for a second to see if that's a clear idea. Because getting around this problem is then the motivation for doing neural adaptation studies and, to some extent, multivoxel pattern analysis. Any questions about this idea? That there could be, that the representation of two different things in the brain might not be detectable with fMRI. It's important to know, right? Because there's all sorts of things that we know just from behavior or perception are different, but don't evoke different responses, right? So for example, I could show a picture, I could put somebody in the scanner, I could be in the scanner, and I could see a picture of Eiling's face, and I could see a picture of Kepa's face, and if I measured the neural activity from the part of the brain that responds to faces, there'd be no difference, right? The average activity to seeing these two people is the same. But of course, I know that there's obviously a brain difference because I can recognize them as two different people. And so the reason why fMRI might show no difference between them is because it's the pattern of firing, right? The actual set of neurons is different, although the amount of activity is the same. Okay. So the important thing to know is that the bold fMRI signal integrates neural responses over seconds and millimeters. It's like the average of a little response over time and space. So if the average is the same, you can't tell the difference, okay? So a final couple thoughts then about thresholding and things just as a background. One motivation for doing this kind of thresholding is that there are many voxels that make up the brain, right, that make up this entire image. So in a typical fMRI study, there might be about 60,000 little dots that make up the picture, okay? If at each of these dots you do a statistical test, right, you say, hey, was there a difference between fearful faces and neutral faces at this point and this point and this point? And suppose at each of those points you said, I don't want to be fooled by noise, so I'm going to say, only show me, I'll only accept that there was a response there if it's p less than 0.05, right? I want it to be significant that there's a difference between those two things, right? But if I had p less than 0.05, that means only 1 in 20 times would I be fooled by noise. If I did that for each of those dots, right, 1 in 20 times I would be fooled by noise by chance, but there's 60,000 chances for me to be fooled, right? That would mean I'd have a lot of dots. I'd have a lot of false positive dots, even if there was no difference between the two conditions, okay? So we use a threshold which accounts for all of the number of dots over the entire brain, all of the voxels over the entire brain, to make it the case so that we wouldn't see an effect unless it was significant over the entire volume of the brain, okay? So that's referred to, there's a lot of different ways of doing this. The simplest and most basic way is something called Bonferroni Correction, which is where you take the statistical value you'd like to have, 0.05, and divide that by the number of voxels that you have, which is a very small p-value, okay? If you don't do that, well, then you end up with some certain kinds of problems. I would say, actually, though, Bonferroni correction is just a very crude way of solving this problem. There's much more sophisticated ways of setting mapwise thresholds that, for example, take into account digital smoothing. This is one reason why smoothing is valuable, because it reduces the number of independent comparisons one needs to correct for. In any event, if you don't do that kind of correction, you end up with this kind of problem, right? Now, some of you probably have seen this before. This was a poster that was presented at Human Brain Mapping just a couple of years ago, and now, just recently, has won the Ig Nobel Prize. You guys know the Nobel Prizes? They're the Ig Nobel Prizes, or Ig Nobel Prizes, which are prizes for wacky, silly things in science. And so these guys just won this prize. So what's this study? These researchers at Dartmouth took a fish, a dead fish, and they put it in the fMRI scanner, and then they did an experiment. They asked the salmon to think about its position in society for 30 seconds, and then they asked the salmon to think about happy experiences it had had in the past, and they had the salmon do this every 30 seconds, the dead salmon, and then they analyzed the data, but did not correct for all the points across the brain. And lo and behold, they found some false positive little points that was active, okay? So this is actually a really basic point. We've known for 20 years longer that you need to do this correction for multiple comparisons for all the statistical tests you do, but the dead salmon kind of helps drive that point home. That if you don't do the correction, you'll end up finding a salmon that is concerned about its position in society. And so I should say, false positives in the human brain, so in human data, are very alluring. Like, you can be easily fooled. So this is data just from a subject who was sitting in the scanner doing nothing, but then we pretended as if he was doing a certain experiment and then didn't correct the data properly. And so if you smooth the data, you get blobs that look very, very real, okay? So it is necessary to do these kinds of corrections for the number of statistical tests. Otherwise, you can get easily fooled. Another way that this has recently been expressed is in something called Voodoo Correlations. This was, again, something that was in the news and got discussed a little bit. There are a fair number of papers that describe a correlation between some kind of behavior and a measure of neural activity across a population of people, okay? So a typical claim might be something like this, that if I take, say, 100 people and I put them in the scanner and I measure brain activity while they look at pictures of sinks, right? So I have them in the scanner, they look at a picture of a sink. And then, separately, I have them fill out a questionnaire, or I observe their behavior, and see how likely are they to wash their hands after they use the bathroom, right? Like, we all know after you use the bathroom you should wash your hands, but not everybody does it. So suppose you were able to find out for a group of 100 people, how likely is it that they wash their hands? And so you have that measure, and then you measure brain activity while they look at a picture of the sink. And then you look across the brain, so you take the data from all the subjects and you put it all into a standard atlas space, and you look across the brain and you say, hey, is there any point in the brain where the neural response, the signal in response to seeing a sink, correlates across people with the chance that they'll wash their hands, okay? And if you do that, and you take the data and you correlate across the brain, you might find a region like this. You'll find an area where the likelihood of washing your hands is correlated very strongly with the bold signal response to seeing a sink. And this has led to the idea that, okay, this is the hand-washing area of the brain, that we can predict behavior very accurately by having a scan like this. Well, there are a number of these sorts of studies that were published, and a researcher named Ed Vole, who was at MIT at the time and is now, I think he's at California in Berkeley, what he demonstrated, or what he argued, was that a number of these studies have a flaw. And the flaw is, if you look all over the brain for a correlation between two things, there's a lot of different points you can test. There's 60,000 chances to find a correlation. And one of those points in the brain, just by random chance, will have a strong correlation. That the noise, just the noise variability between people, happens to line up with the chance of hand washing. Okay? So just by probing or looking around through the noisy brain, you'll just happen to find a point where those two things are correlated. And then if you make a plot like this, it looks very convincing. But all you've done really is you've just searched through noise until you've found something that happens to correlate. Okay? And this is what he referred to as voodoo correlations, like the belief that you've actually discovered a relationship that's true when really it was just the result of noise or bad luck. So you need to correct for all these comparisons that you've done across the brain to not end up with a mistake like this. Any questions about this idea? Yeah?
You said Bonferroni Correction was a very good way of going about it.
So what are the other methods to it? Now, so this is a potentially long topic, and it gets really boring. But so let me say that, give this as a background. For many years, the field of functional MRI was very concerned with how to set that threshold for within subject data and to make it accurate. So if I scan just you and I get your data, how do I set a threshold so I can make a claim about significance for just you? So that was a very big, important question in the field for many years, and we came up with some solutions which involve it's some complicated math. It uses what's called the Euler number of the space and topology and blah blah. There's some ways of doing it, and so it's a technique that's built into SPM, and it uses a solution introduced by Keith Worsley some years ago that takes account of the smoothness of the data over space and the distribution of the values, statistical values that one would get of the T statistics across the whole brain. Anyway, so that's this one technique. The reason I won't go into great detail about it is because it's not that important anymore, because it's very rare that any of us would do a study where we want to get the data from just one subject and then look at the activation and make a claim about significance across the entire brain. What's much more common is that we do a test with 10 people or 100 people and then make a claim about a significant activation across the group. And there, the solution or the modern technique for solving this is using permutation or bootstrap techniques. Okay? And the way that is done is if you have the data from each of many subjects, suppose you have, that's the bad one. Suppose you have now data from, my brains are not looking good. That's better. Okay, so you've got brains which are these are now the controls, and these are the psychopaths. Okay? And suppose you want to make a claim that there's some point in the brain where the activation in the controls was bigger than the activation in the psychopaths. Okay? That's the claim you want to make. And so you kind of get all these brains into a common space, and you make a statistical map where the value at each point in the brain was how big on average was the difference, right? So if we take just this point and we say that the controls had a value of, like, they had a 3% signal change to the fearful faces and a 2% and a 1.5% change, and the psychopaths at that point had a 0.5 change and a 1% change and a 1.2% change. Okay, and I do a t-test between these, then at this point in the brain, suppose there's a t-value of 4.7 for the difference between psychopaths and controls, right? So that might be how you'd create this map, and then you do this for every point in the brain. Now the question is, how do you know that that t of 4.7 is significant, all right, for the whole brain? The way you solve this problem, and this was introduced by Tom Nichols, was who originally described this for fMRI, is you reanalyze the data, but you randomize whether somebody is called a psychopath or a control. Okay? So you pretend as if, right, this person was actually a control and this person was actually a psychopath. Right? You relabel the data and you analyze it again and you say, how big was that t-value there? Okay? And you do it again for a different ordering of the labels. Okay? Because you have the labels of controls, you know, C1, C2, C3, and P1, P2, P3. You randomize the labels, analyze the data, randomize the labels, analyze the data. And for this point in the brain, you'll then have a distribution of values centered about 0. Okay? Because if you randomize the data completely, there's no possible difference between the groups, right? Because the groups are intermixed. You've mixed them up. So the t-statistic you get is going to be if you measure the t-statistic at that point across all the different randomizations, you get a distribution, and you say, okay, well, only 0.05 of the values were bigger than this point, and my t-statistic fell here for the real ordering. Okay? And so that's how you say that this is significant. It's better than any of the randomizations. And you do this not for just one point, but you do it across the entire brain. Does that make sense? Yeah, so this permutation approach is really the way that group analyses are now done for assessing significance, because it automatically takes into account the smoothness of the data and sort of the effects across space. Any questions about that? Okay. All right, so how are we doing on time?
11.
11, perfect. Let's take a 5 or 10 minute break, and then when we come back, a little bit about inference, and then signal and noise properties. 15 minutes or so, I'd like to address how we go from a well-made brain picture into a claim about somebody's mental state. Okay? You've already seen this 3 times. Okay, the big point of what I'm going to tell you is that there are 2 basic types of fMRI or neuroimaging experiment in general, right? There's just 2 basic types, and each type of experiment makes different assumptions. And so if you understand the assumptions that are being made in the experiment, you'll be able to know whether or not the experiment was good or bad and the quality of the claims that are being made. Okay? And then in addition to those 2 types, there's a 3rd type of experiment that combines the 2. And this is just to foreshadow, that's the Mvpa type experiment. Okay. So let's go through just some quick examples. So the first type of experiment makes claims like this, that we have found the brain area for love, right? Like this part of the brain, this is the brain area for love. These kinds of claims are of the type of what's called forward inference, right? Which is you make a claim that there is a brain area that corresponds to an isolated behavior, right? So when this person is in the mental state of love, this brain area responds, okay? There are many sorts of claims or studies like this. I just found some examples from looking at a couple of magazines in the United States called Time and Newsweek. These are like these popular magazines, and they often report on fMRI studies. So here's some examples of claims that they made. So here's the first one. So they have things like why we love, this is your brain on optimism, and something about fMRI of menopause, which I don't know why someone would study that. But so here are these claims, like being in love activates the ventral tegmentum and the nucleus accumbens and the caudate, which is so romantic. Optimistic people activate the anterior cingulate when thinking about future rewards. Okay, that's another kind of forward inference claim. Or a menopausal hot flash increases activity within the insula. I don't know why people study this, but that's it. So this is the way these studies are done. Here's how a forward inference study is done. As you know, in an fMRI study, you have to subtract between two behaviors, compare two behaviors. So in a forward inference study, you isolate the behavior of love by comparing two things. And so one way you might do this experiment is compare the brain response to seeing pictures of your wife to seeing pictures of your friend, right? That might be one way you might try and isolate love, right? So what that experiment might look is that over time, you look at pictures of your wife, and then for another 30 seconds, you see pictures of your friend, and you do this back and forth, and so you get the sort of brain activity response of pictures of your wife and pictures of your friend. And the idea is that if you compare between these, you're left with love, right? Now, of course, just from this cartoon example, you can think of all other sorts of things that might differ between the two conditions besides love. All sorts of other things might be different about seeing these two pictures, okay? And so that's the key problem for these forward inference studies, right? It all hinges on how much you believe that you've isolated this particular behavior. And so when you go to critique or think about these sorts of claims, really most of the intellectual work comes at trying to isolate the behavior. Now, in studies of cognitive neuroscience, these problems are, of course, there as well, beyond just sort of studying emotional states like love. A classic example is the study of a mental operation like working memory. Okay? Working memory is the mental operation that is thought to occur after you hear a piece of information or take in a piece of information and have to hold it across a delay until you can act upon it, right? So working memory is holding information across a delay. And a classic kind of task that is used to evoke working memory is like this, that you stare at a fixation point and there's a dot. You have to remember where the dot was. There's a delay of some seconds, and then a little circle comes up, and you have to say, was the dot in that circle space, right? That's a working memory type of task. So if you wanted to study working memory in the scanner, how would you, and you think working memory is happening during this period. That's the working memory period. So if you want to study working memory, how do you isolate that behavior? How do you find it? Bless you. So the tradition is to do what's called a task analysis. And so you compare one version of the experiment, one version when the subject is in the scanner, of holding information across a delay, and then a control task where there is no delay. They see the stimulus, and then they respond immediately, and then this delay happens later. Okay? So up there, that includes working memory, but down here, no working memory. Okay? And so the way that this is justified to say that we have isolated working memory is you do what's called a task analysis. You say, okay, in that top state, you see the stimulus, there's working memory, and then you make a response. But down here in this control condition, you see the stimulus and you make a response, but there's no working memory. Okay? So if you take the difference between the two, all that's left is working memory. So this kind of design or this kind of approach makes the assumption of something called pure insertion. Okay? And this is the assumption that you can add working memory in between seeing the stimulus and making a response and not change these mental operations. Okay? The idea of that is you can add this piece of holding on to the information across a delay, but seeing the stimulus isn't changed by that, and responding to the stimulus isn't changed by that. That assumption is called pure insertion, okay? That you can just add it right in. But here's the thing. If that might not be true. What if after you have to hold the information in memory, when it comes time to respond, you push the button a little harder than if you didn't have to hold on to the information in memory, right? Or when you see the stimulus, you stare at it a little longer when you need to hold on to memory or not. Or there's some interaction between the memory component and the other pieces. And that might fool you into thinking that you've isolated working memory and found the working memory area of the brain, but actually you found the area of the brain that is used to push buttons. Okay? So that's this assumption that goes into this approach of cognitive subtraction. Now, of course, the field is much more sophisticated than doing these simple comparisons. You know, another kind of approach that's used to get around this problem is what's called a parametric manipulation. So instead of trying to just take the difference between two things, you try and modulate or adjust the amount of working memory. So you have three versions or three conditions in your experiment where you have to hold one thing in memory, and then another version where you hold two things in memory, and another version where you hold three things in memory. And then you look to see, is there a brain area where the fMRI signal is related to the number of things you had to remember, okay? It turns out this doesn't completely get rid of this pure insertion problem. You could still get fooled. You could still press the button harder after holding more things in memory than one thing in memory. But this is science. It's supposed to be hard. But the main thing to be aware of is that when you make this claim about this is the brain area that responds to this mental operation, the key question is, well, how well did you isolate that mental operation? Okay? And to a large extent, when I go to critique fMRI studies, or if I think about what's wrong with an fMRI study, the problem usually isn't like how much did they smooth their data, or how much, you know, how did they line the brains up in space. The problems are more of this type. How well did they isolate the mental operation? Okay? And as you design your own experiments and think about these things, it's worth keeping in mind the difference between a task and a mental operation or a cognitive process. Okay? Generally, we're interested in cognitive processes or mental operations, working memory, noun retrieval, love, things like that. But we have to use tasks and stimuli to get at that. Okay? And so in forward inference studies, it's the relationship between these two things that's really critical. Okay? So when you design an experiment, you design tasks, but you're trying to isolate a mental operation. Okay? It's worth keeping in mind that the result of a forward inference study is not the same thing as the result of a lesion study. Okay? So you could say that suppose I did my study and I found this is the brain area that activates for love, right? If I now took that subject and I went in and removed that part of the brain, would they no longer be able to experience love? That's the question. And the answer is not necessarily so, okay? It turns out that you can get an area of the brain that activates to a mental operation, but it doesn't necessarily mean that that brain area is needed for the experience of that mental operation. The reasons for this we could talk about if you like. It has to do with the fact that there could be other, you could have two brain areas that activate in parallel, and you could take out one and the other one could still do it. There's many reasons why, but just as a general rule, the results of a brain imaging study are not the same things as the result of a lesion study. The two things give different kinds of information. Okay? And finally, along this way of like varying sort of parametric approaches, you can do this not only within a single subject, vary the amount of the mental operation, right? So in this case, try and put this subject in the state of more love or less love and look for a related activity. But you can do this across subjects as well, right? So you could try and vary the amount of love that people experience. You know, maybe this guy just has a new girlfriend, and this one's not so sure about how things are going. And so you then look across the group to see if there's some relationship between those things. Okay? So this is sort of the typical approach that's used in these studies, as you vary something parametrically. So for these forward inference studies, the real key question is, how was the behavior isolated? Okay? So that's one type of study. The other type of neuroimaging study is what's called a reverse inference study. Okay? And I've written a bit about this. Russell Poldrack has written an awful lot about this and is quite well known for his thinking in this area, if you want to read more about it. But a reverse inference study is of this kind. So it might make the claim that like hearing a bad joke causes physical pain, right? So if I tell like a real bad joke, the way you feel is just the same thing as if I hit you with a hammer, okay? It's the same kind of feeling. And the way that claim works is, I tell you a bad joke, and if I see activation here, which I know is the brain area for pain, then I conclude that you are in pain, Okay? So I look into the brain and see the activation and then make a claim about your mental state. And that's why it's a reverse inference. I'm going from the brain back to your behavior. Okay? And so that's what you want to do. You want to use local brain activity to identify a mental state that a situation evokes. And there's many sort of big claims or sort of studies that use this kind of inference. So these are some examples of these sorts of things, how we get addicted inside the grieving brain. Just some examples of this. It's like untrue statements make us feel disgust, just like seeing rotten food. That was one study that was quite good. It was looking at the activity in the insula. People with complicated grief, so people who are still mourning someone who has died, they experience paradoxical pleasure during sadness. That is, people who are grieving and sad actually have this strange, they almost enjoy the experience. That's the claim. And then there's even been studies of things like why we like to scratch, why scratching feels good. So there are many of these sorts of studies. So what's the key assumption or problem here? Well, the key problem or assumption is that this brain activity means that the person is experiencing pain, right? There could be other things that activate this brain area. Okay? So if this brain area is actually activated by pain and confusion, that would do it. Or is activated by pain and fear or unpleasant memories or anything else. So your ability to claim that this activation means pain depends upon only pain activating this area. Okay? And you might ask, what's the way that you could accumulate evidence in support of that? I'm going to skip this slide. But actually, and that one too. So the way that you would gain that evidence that that brain area is for pain is you would need to have some other evidence to support it. You would need to do a number of forward inference studies, for example, where you would put somebody in the scanner and you'd hit them with a hammer and then see the brain area activate, and you'd put them in the scanner and you'd burn them and see the brain area activate. So okay, so now you know that pain activates it, but you would also have to know that no other mental state activates it. So you'd have to put them in the scanner and tickle them and say, yep, no activation. And put them in the scanner and, show them pictures of cats. No activation, okay? So if you can so that's what's required in principle to make that claim, is that this brain area activates for just pain and for nothing else. And you can see that that's a very difficult claim to support, but for certain brain areas, there's reasonable evidence of good specialization, and so some of these studies are well-based. It's a tough threshold to meet, okay? The final type of neuroimaging study combines that forward inference and reverse inference together. And these are multivoxel pattern analysis studies, and these are very powerful. Okay, so the kind of study is like this, where you would use a brain activation scan to determine if somebody's lying, for example. Okay, and so there are many examples of this, of the category that mind reading is now possible. And this is not such a ridiculous claim for some of these studies. So fMRI data can determine what tool you're currently thinking about, right? So you think of different tools and you can decode that. This was an amazing study from Jack Gallant's lab, which showed that you can look at the visual cortex and know which of 10,000 different pictures somebody's looking at. So you can read out the contents of visual experience from the back of the brain. And in a follow-up study, Jack Gallant has shown, and his team, that you can decode a movie that somebody is watching from the pattern of activity. So that can be done. And then along the lines of this, claims that the scanner can determine if you're lying or telling the truth. So how do these studies work? Okay, these are multivoxel pattern analysis studies, and these studies are done in 2 steps. Okay, step 1 is that there is a forward inference study. So this is the idea that you take the subject and you put them in the scanner, and then you have them do something a few times while a computer learns about brain activity. So here's how it works. You put the subject in the scanner and you ask them to either lie or tell the truth about a card they've picked. Okay, so they pick a card, and suppose it's the 10 of diamonds, and they say, I'll tell the truth. It's a 10 of diamonds. Okay? You instruct the subject, then you say, okay, on this, now lie. So they pick a card, and it's one card and they lie about what the card is. Okay, so you tell the subject to tell the truth or to tell lies while they pick these cards and look at them. Okay? And then you take a look at the pattern of brain activity, right, across the entire brain or in a region, and you train a computer to learn the pattern of activity that's evoked by telling lies and evoked by telling the truth. Okay? So what's the difference in pattern across the whole brain between telling lies and telling the truth? And the details of this are very interesting and important in involving, like, do you use machine learning algorithms and support vector machines, and so that's a sort of a more advanced topic. But in general, you try and train this computer to tell the difference between these two things. Okay, and then so you have the lies and you have the truth, and you learn these different patterns. But then step 2 is you try and decode that information. Okay, so that first step, that was a forward inference. Now we're ready for the reverse inference, which is that you put the subject in the scanner and you now say, okay, you decide if you're going to tell a lie or tell the truth. So the subject picks the card and they say, I picked the 3 of clubs. And now you need to use the brain activity to guess, did the subject lie or did the subject tell the truth? And you look at the pattern of brain activity and see, does it match more the lie pattern or the truth pattern? Okay? And that's how these techniques work. You train a classifier, or you train a computer using data from the subject, and then in step 2, you try and decode something new. Okay? The real key question is how well this generalizes to things that you didn't train on. Okay? So if you train the computer on lies and truth about cards, can you decode other sorts of things like, I never stole money from the supermarket, or I, never cheated on my girlfriend, or things like that. Okay? Can you decode that other kind of information? So the real key limitation or question to ask about these kinds of decoding studies is, can the classification generalize beyond the training set? Right? Beyond the things you've trained for, can you decode new sorts of things or new sorts of information? And that's where the study takes you into having learned something new. Okay? So this is multivoxel classification. I think this is an incredibly powerful technique that is becoming very important within the field. And the reason it is so powerful is it combines a forward inference study to sort of look at the relationship between mental states and an area of activation, and then a reverse inference study to try and then get back to something about behavior. Okay? So those are the 3 sorts of studies: forward inference, reverse inference, and multivoxel classification. By the way, all of these slides and other slides from my talks are available on my website, so if you ever want to try and download those and get more information, you can look at those. So let me stop there. Any questions about forward inference, reverse inference, these ways of using a brain scanner to look at the relationship between brain and behavior? No? That's all good? Okay. Yes?
Just a curiosity. Like in the Multivoxel classification, can you use a neural network to predict, for example, associate outputs, like a neural network PDP model, so to predict? So make this kind of training with voxels and then predict.
Right. So the question is like, well, what exactly do you use for this training stage? Like, what's the model?
It would be qualitative, right? You can do it more accurate, but maybe there are like probabilistic models.
That's right. Well, no, that's right. So the question is, well, okay, so how do you do this training? What constraints do you put upon the computer, or what model does the computer use to do this learning? And that's actually where a lot of the particular inferential power of these studies come from. So for example, in that decoding study of vision from the cortex, it was shown that using a model which knows something about how neurons process visual information made the model better. So if you use a computer model that takes advantage of your knowledge of how neurons work, then you do better at training and better at classification, right? And you can show that it does that an accurate model does better than an inaccurate model. There's been some very nice work that's been done by Hans Optebeek, who's at the University of Leuven in Belgium, and he used a neural network model that he trained to be able to read individual letters and know that an uppercase A is the same as a lowercase a. And he had multiple hidden layers for that neural network model. And then he showed that if you do this multivoxel pattern analysis, that different regions of the brain correspond to the different layers of the model. So that's a validation that the model is an accurate representation of how letter reading works, for example. So this is a huge field with lots of these sorts of things, but this is sort of the general structure of the claims that are made there. Okay? So, and how much time do we have left? What time is it?
25 minutes.
Oh, all right. How you guys holding up? Okay. All right. So here's what I wanted to talk about then in the final 25 minutes is a little bit about signal and noise and Fourier transforms and these sorts of things. Okay. So first off, so I asked on the first day who knew anything about a Fourier transform, and I think I saw 2 hands. Do we have any more hands today? Does anybody know about the Fourier? Let's see. Oh, there's 1 more, 2 more. Okay, good. So some people took a look into it. So okay, here's the idea of a Fourier transform. Okay, so now we're getting ready to move into advanced fMRI. By the way, congratulations. You've all graduated from basic fMRI. Give yourself a round of applause. Well done. We are now ready to move to advanced fMRI. And so our first lesson in advanced fMRI is the Fourier transform. Boy, you're going to wish you were back in basic fMRI. Okay, so the Fourier transform. Here's the basic idea. This is such a neat idea. So first off, you should know that this guy Fourier was a really cool character. This was a Frenchman who's famous in 2 completely different areas. He's famous in mathematics, and he's famous in Egyptology, right? The study of hieroglyphs. He actually worked with, when Napoleon was doing all his Napoleon things, Fourier actually was the person in charge of interpreting all sort of Egyptian artifacts that sort of made their way back to France. And he made great progress in interpreting hieroglyphics. So he's very famous in circles of Egyptology. And he made this fundamental advance in sort of the mathematics of analyzing signals. Okay, so here's the idea of a Fourier transform. All right, so you guys all know that this shape, which is a sinusoid, right? So a sinusoid, it's just a trigonometric function that has sort of a wave pattern to it. Okay, and sinusoids can be described by their amplitude, which is how big it goes up and down this way, and their frequency, which is how long does it take to go from one point to the other. Okay, so you can have sinusoids which are the same frequency but have a small amplitude, which I cannot draw very well. Sorry. So that's a small amplitude at the same frequency, and you can also have sinusoids that are higher or lower frequencies, right? So that's a higher frequency because there are more peaks per unit time, okay? So a low frequency sinusoid is one that slowly changes up and down, and a high frequency sinusoid is one that goes up and down very rapidly. Okay, here's Fourier's insight. If you take any signal in time, you can express that signal equivalently as the sum of sinusoids and cosines, but we won't talk about those, the sum of sinusoids of different frequencies and amplitudes. Okay? So here's the basic idea. This is time on this side, and this is going to be Fourier space, or the Fourier transform on this side. So we'll call this Fourier. Okay, so if you have a signal in time that looks like this, it can be represented as the sum of a set of sinusoids. So it turns out to get this, you add in one sinusoid that looks like this, plus other sinusoids at higher frequencies that kind of get these little corners. So like one that's like this, and one that's like this. And if you add together these 3 curvy lines, you'll start to get something that looks like this box. Okay? So any signal in time can be equivalently represented by the sum of a set of these sinusoids of different frequencies, okay? And a way of summarizing that representation is in something called a power spectrum. And in a power spectrum, it's a graph where you have low frequencies and high frequencies. And you show how much of an amplitude was there of this low frequency sinusoid, and you make a dot here. And how much amplitude was there of this higher frequency one, and that higher frequency one's like that. So this is amplitude along this axis. Okay? So I can show you another more basic example. If you had a signal in time that looked like this, right? That's the signal in time. You can see clearly that that's the sum of one sinusoid that's like this and another sinusoid that's like this, right? You can see if you add these two things together, you'll get that, okay? So a way of representing that as what's called a power spectrum. Whoops, I'm sorry, for those who are on the side of the room, spectrum. So the way of representing that as a power spectrum is that you have one low frequency, which is a big one, and one higher frequency, which is a small one. Okay? So the key idea here is that it's a way of describing for a signal in time how it is being modulated at low frequencies, things that are changing slowly, and high frequencies, right? So this signal here, we can say, has a lot of power, or has a lot of things happening at a low frequency, and has also a little bit of energy or power at a higher frequency. And the really amazing thing, and this is, Fourier's key contribution, is that any signal in time, no matter how kind of complicated or wavy it looks like, can be decomposed or represented as a Fourier transform like this. Okay? So the reason I wanted to introduce this is because there are some aspects of fMRI experimental design that are easier to discuss or understand within the context of a power spectrum representation. Okay? It's easier to talk about some experiments and the properties of fMRI data for this kind of representation. Okay? So when you see this, what you should interpret it as is the higher the peaks are down at this end, that means how much things are changing really slowly over time. And up here, it's how much things are changing rapidly. Okay? So that's the basic introduction to a Fourier transform. So what I want to talk about a little bit then for the remaining 20 minutes or so we have today, and then as we go forward, is how an understanding of the signal and noise in fMRI data expressed as sort of these power spectra lead you to have better or worse kinds of experimental designs. Okay? So this really falls in the category of designing an experiment, how to arrange events in time. And so one kind of dichotomy or sort of different approach that you can take in fMRI experiments is between something called a blocked and an event-related design. And these are sort of terms that have been around for a very long time that represent kind of prototypical experiments. And so they're useful kind of categories to organize our thinking. So, okay, so a blocked experiment is where you have events which are arranged in low-frequency blocks, 30 seconds of seeing faces, 30 seconds of seeing houses, 30 seconds of seeing faces. And event-related, where it goes house, face, face, house, face, right? More of a random approach. So what we'd like to work towards is understanding why one design or the other design is better or worse and what they're good for, okay? So we've seen before this kind of plot of the hemodynamic response function, okay? So this again is if there's a point of neural activity here, over time the signal rises and falls, right? And it does so slowly. Another way of expressing this plot is as a Fourier transform or power spectrum representation of it, okay? And that looks like this. So what does this plot mean? Let's go through it. So this is that same hemodynamic response function now shown as a power spectrum. So what's being shown here is that this is the amount of power, the amplitude of that response at low frequencies and middle frequencies and high frequencies. And so this describes the ability of the hemodynamic response function to pass neural activity at different frequencies. What this means is that if there was a change in neural activity that was happening very slowly, like it rises and falls over a minute, right? Then that is a change in neural activity that the hemodynamic response function could represent well, right? So that would carry over into the fMRI signal. But if there was a change in neural activity that was happening fast, up and down, up and down, up and down, then that would not pass well into the fMRI signal. So this x-axis is expressed in terms of frequencies or hertz. We can kind of turn that into sort of periods of time. So it turns out that about here is 30 seconds on and 30 seconds off, 30 seconds on and 30 seconds off. And all the way up here, off the scale at 1 hertz, is something that's going up and down every second, right? So 1 hertz is it's something that's changing every second, okay? So what that means then is that only changes in neural activity that happen slowly will be detectable by fMRI. If something is changing up and down faster than about every 4 seconds or about every 3 seconds, then the hemodynamic response function can't keep up with it, and it won't pass it through into the bold fMRI signal. Okay? So knowing this property of the fMRI data would tell you that you should design experiments where changes happen really slowly, right? The best kind of experiment for fMRI would be one where you have like 5 minutes of faces and then 5 minutes of houses and 5 minutes of faces, right? So if this is all you knew, that would be the best design for fMRI. But that's not the whole story. The other half of the story is the noise that's present in the data, okay? So now what's this plot? This is a plot of the power spectrum of the noise that's present in fMRI data. And so let me tell you how this got made. So if you take a group of subjects and you put them in the scanner and you have them do nothing, you just sit them in the scanner and they can close their eyes or stare at a blank screen, and you just let time pass, and then you take the signal from each point in the brain and you convert it into a Fourier transform, or at a power spectrum, and then you average those power spectra across all the points in the brain, you end up with a plot like this. So what does this mean? Again, this is frequency along this axis, so these are low frequencies and middle frequencies and high frequencies. And so what this shows is that when subjects are sitting in the scanner and not doing anything, they're not doing an experiment, there are signals that rise and fall very slowly across the entire brain, okay? And there's more and more and more of this kind of drifting and changing of the signal at ever lower and lower frequencies, right? So that the signal from one point in the brain, just to make this very concrete, so if you have a subject in the scanner and they're just resting, and you take that point and you make a plot of the data over time, it looks something like this. Right? So just like slow oscillations up and down. Okay? Lots of sort of drift in the signal up and down over time. So this is low frequency noise. Low frequency noise. Okay? And if you then take that and represent it as a Fourier transform, you'll see there's lots of power up here and then not as much as you come down to high frequencies. Okay? And so that's what that representation is. It's a representation of the intrinsic noise. It turns out that this function is well fit by a 1 over frequency squared curve. So if you can fit a function to this which has the form, the mathematical form of 1 over the frequency raised to the power of 2. And that has very interesting implications for what this noise is like, and we could get off into a big discussion about that. It turns out that's what's called red noise or Brownian noise. Happy to talk about that over a beer later on. But in any event, this property of the bold fMRI data means that there's lots of noise at low frequencies. Okay? So if you put somebody in the scanner and you had them do nothing, but you pretended as if they really were doing some task, right? Suppose you said, I'll have the subject in the scanner and I'm going to have them, spend 30 seconds looking at pictures of houses and 30 seconds looking at pictures of faces. But, the projector was broken. They didn't actually see any of these things, okay? If you then analyze the data, you'd end up with false positives, right? because even when the subject was doing nothing, the signal was rising and falling, right, with a time course that could look like your experiment by accident. And so we know about this property. We can measure this noise feature of the data. And so in fMRI data analysis, this property is corrected. You actually correct and sort of remove this noise component. But the consequence of that is that it makes it very hard to do experiments where the neural activity changes very slowly. Because by the time you remove this noise, you remove a lot of the effect that you're trying to measure with your task. Okay? So if you knew only this, if you only knew about the noise of the fMRI data, then what you would say is, well, the best design is one where things change really fast, right? I'd like to avoid all that low frequency noise. So I'll design an experiment where, 2 seconds of houses, 2 seconds of faces, 2 seconds of houses, 2 seconds of faces. That would be all the way down here in the low noise range, okay? We'll come to a little bit during the journal club why this is better with arterial spin labeling or perfusion. But for now, the main message I want to tell you is that fMRI experimental design is stuck between, in English with the expression, a rock and a hard place, okay? You're stuck between the hemodynamic response and this intrinsic noise. The filtering properties of the blood flow response say, design an experiment which has slow changes in neural activity. That's the best, okay? The noise in the data says, design an experiment with high frequency or rapid changes in neural activity. That's the best. So how do you balance off between these two things? Well, it turns out the sweet spot, the best balance between these two effects is a signal that varies about every 20 seconds on, 20 seconds off, 20 seconds on, 20 seconds off. That's the best balancing point between the filtering properties of the hemodynamic response function and the noise that's present within the data, okay? So that's the reason why when you look at an awful lot of fMRI experiments, particularly the classic types that have this sort of blocked design, that they all seem to have this design where something happens for 20 or 30 seconds and then you switch to a different thing and then one thing and then the other thing. So like why is it always 20 or 30 seconds? Like why is that the magic number? And the answer is because it's a compromise between these two problems, right? Between the signal and the noise properties of the data. How much time do we have left? What time is it?
5 minutes.
Perfect. So let's have some questions about this. So any questions about the signal and the noise properties of bold fMRI data in time and in frequency representations? People sometimes ask, like, well, what is this noise? Like, what is this stuff? Why is it there? So actually, this is the raw material, right, that is now used today in analyzing and understanding resting state studies, right? So for years, we tried to figure out, like, why, like, what is this noise? Why is there this, like, low frequency fluctuation across the entire brain? Could it be that these are just fluctuations that are related to the heart rate and breathing that produce all of this? It explains a little bit of it, but not all of it. So it turns out that even if you model and remove cardiopulmonary activity, right, so activity of the heart and lungs, you still have this 1 over frequency squared increase in noise. It's still there. You can reduce it a bit, but it's still there. What are some other properties of it? Well, one interesting property of this noise is that it shares phase over space. That means that the fluctuation that's happening in one part of the brain is matched up with the fluctuation that's happening in another part of the brain far away, way across the cortex. Okay? And at the time all this was described and discovered, back in the mid-1990s, we just thought this was an annoying and frustrating part of the brain. It's just there to mess us up and make it harder to do experiments. But what we now know is that these fluctuations are actually linked neural activity of the brain at rest. Okay? So that when you're not engaged in doing a task, brain activity in different areas of the brain, it's communicating with one another. And that an analysis of those fluctuations can be informative about how different brain regions are connected to one another. This is the basis of these functional connectivity studies, where you have somebody in the scanner resting and you measure the fluctuation, this low frequency noise, and show that different areas of the brain are correlated with one another. So that's an important property of the data that can be used for resting state studies. But if you're doing a task study measuring activation, then this property can mess you up. You have to model it and get rid of it. Okay? And so in functional MRI software like SPM and FSL and all those things, they all contain techniques for modeling and removing this, this effect in the noise. One other thing to say about this noise is that it violates a key and basic assumption of most statistical analyses. Okay? So when you do a statistical test, it assumes that, that the noise is flat, actually, that it's like white noise. What that means is that there is no systematic fluctuation in the data over time. That's actually a key assumption of most statistical tests, that the observations are independent in time. And so fMRI data do not satisfy that property, which is why you need to have special statistical models to analyze fMRI data. And those things are built into, again, SPM and FSL and other statistical packages. Okay? So all of those contain a step which is sometimes called a pre-whitening step, or the data are modeled with what's called an autoregressive function to try and fit this noise and remove it from the data so you can then make valid statistical inference. Okay? All right. So the final thing then I'll say about sort of the relationship between these two things and the trade-offs are that this leads to a trade-off between estimation efficiency and detection power generally. But let me just say that the key thing that is challenging in experimental design is dealing with sort of randomness. So a block design, so I won't go into all the nitty-gritty, but a block design has the property, that it can be perfectly positioned between the noise and the signal. Okay? So if you have 20 seconds on, 20 seconds off, 20 seconds on, 20 seconds off, that's perfect. That's going to be the most powerful fMRI design you can have. That maximizes your chances of measuring neural activity. Okay? If you have the neural activity vary on a 20-second cycle. However, it's kind of predictable, right? So if you are sitting in the scanner and you see 20 seconds of faces and then 20 seconds of houses, you kind of know that coming up next will be 20 seconds of faces and then 20 seconds of houses. And there's certain kinds of experiments that's no good at all, right? Suppose you're studying memory. You wouldn't want, if you have somebody learn a list of words, and then you're going to put them in the scanner, and for 20 seconds they see old words, and for 20 seconds they see new words, the subject will kind of notice that it's all the old words are together and all the new words are together. Sometimes for psychological design reasons, you'd prefer that the stimuli are randomized. Okay? And that leads to then the desire to have an event-related design where you randomize the order of old words and new words or houses or faces. But the problem there is that a random ordering of stimuli puts power at higher frequencies as well. So for that reason, event-related designs are less statistically powerful. Okay? There are sort of some advanced techniques that you can use to create an ordering of the stimuli which looks kind of random. It would fool most people into making you think it's random, but that it actually has a pattern that's at these sort of lower frequencies. And this is some work that I'll describe a little bit more, I think, on Friday, that can be used to sort of hide in a random pattern a modulation or a variation which actually is at a low frequency, so it's detectable by fMRI. Okay? All right, so the very final thing I'm going to say, and this is going to be a preparation for the journal club this afternoon, is that one way to escape from this problem of the low frequency noise is with a technique called perfusion Fmri. And so perfusion Fmri is really clever. This was invented by a guy named John Detra, who's at the University of Pennsylvania, as well as Alan Koretsky and others at other institutions. So here's the approach. The approach is that instead of measuring the change in signal at a point in the brain from the amount of oxygenated or deoxygenated hemoglobin, Perfusion Fmri uses a totally different approach. The idea is that you can set up a magnetization gradient, right? So a magnetic gradient that you know what the frequency of the protons are at this point in the neck, right? So you say, this is going to be 64 megahertz right here at the neck. And then you put in radio waves tuned to 64 megahertz, so all the protons in the neck get tagged, right? So all the protons in the neck have that 90-degree pulse just in here, okay? But those protons in the neck, they don't sit still, because some of those protons are sitting in blood vessels in the carotid arteries, and so they flow up into the brain. And then, after a delay, you can read out the effect of that tag up here in the brain, okay? So you use a slice-selective magnetic field to label inflowing protons and then measure out their effects in the brain. And the end result of this is an image of the brain, after doing some math, where you're measuring how much blood flowed to one point of the brain or another point of the brain. And this is a measure of a physiologic property called perfusion. And so perfusion, now that has units. We can talk about perfusion in terms of cc's of blood per grams of tissue per minute, like in actual physiologic units. So most brain tissue has a blood flow of about 90 on this scale, right? And it's an actual quantifiable number. So the way that these sorts of images are made is by taking a series of images, one after the other, where you have one image which has the label done and flows up into the brain, and then the next image which doesn't have the label, and then an image with the label that flows up. And then you take the difference between those. Oh, shoot, that didn't turn up. Let me show you this. Okay, what you do is you pair the images together and then take their difference, and that yields this blood flow measure, okay? So by taking initial sort of label, control images of the brain and then subtract adjacent images, the resulting images here, these are now perfusion images. These have this measure of blood flow. And if there's increased neural activity in a part of the brain, the blood flow will increase and then fall back down. And that's something that could be measured in this time series. But the key thing, the real important property about this kind of time series data for fMRI is that 1 over f noise goes away inside this time series data. And the reason is because when you subtract adjacent images, what you're doing is you're taking, say here's like this low frequency noise that's present in the brain. You take the difference between these 2 points and the difference between these 2 points and the difference between these 2 points and between those 2 points, and that effect removes this big drift. Now this is just, once normalized, the difference between these two is like this, and then this, and then this, and then this, and then this. So this signal, which is the difference between adjacent points, removes that low frequency drift, okay? So as a consequence, if you look at perfusion data collected while someone just sits in the scanner and does nothing, instead of having a 1 over f function like this, the data looks flat. It has a flat or white power spectrum, okay? And the consequence of that then, to sum all that up, is that perfusion imaging is very good for measuring slow changes in neural activity. In fact, it's perfect for that. You can use perfusion imaging to measure something neural activity that slowly increases over an hour, right? So an hour of an increase versus a drop. And there's certain kinds of behaviors that you might be interested in that change very slowly, like emotion or learning, right? Where there's a very slow change in the neural signal that you'd like to get. And so perfusion imaging is just ideal for that. And so this afternoon in the Journal Club, we'll talk about this one paper that was led by Ingrid Olsen and that I helped out with, which was a measure of learning of a pattern sequence that we were able to detect using perfusion fMRI. Okay? So we'll stop there. I think we're just up on noon. Thanks very much. And for anyone who's making it to the Journal Club, I'll see you at, 3:30? All right, great. See you guys tomorrow.